So our first example here is going to be for the magnitude angle notation. So we have a hedge maze is a maze formed by tall rows of hedge. After entering, you search for the center point and then for the exit. The figure shows an entrance to such a maze and the first two choices we make at the junctions we encounter in moving from point I to point C. We undergo 3 displacements as indicated in the overhead view. We have D1, which is this one right here. Whoops, that's not it. This one right here. Rowdy, stop barking. And our angle right here is 40 degrees. We have D2, which is this one right here, and our angle is this one at 30 degrees. And then we have D3, which is 5 meters, and it's just straight to the right with an angle of 0. Where the last segment is parallel to the superimposed x-axis. We reach point C. What are the magnitude and angle of our net displacement d net from point I? So let's take these one at a time. I'm going to start with D1. So this one is up like this. Our angle is this angle here. This is our D1, which is 6 meters. And then we have our D1y and our D1x. So solving for our x and y components, let's start with D1x. That's going to be the cosine because it's the adjacent side to that 40 degrees. So we get the cosine of the angle is equal to D1x adjacent over D1 hypotenuse. So we get D1x is equal to D1 times the cosine of the angle. Plugging in our numbers, we get D1x is equal to 6 meters times the cosine of 40, which is equal to 4.6 meters. Doing the same thing with D1y, we get the sine of the angle because sine is opposite, D1y over hypotenuse D1. And then multiplying D1 times by both sides, we get D1y equals D1 sine of the angle. D1y, plugging in our numbers, we get 6 meters times the sine of 40 degrees. Plugging in our numbers, we get D1y is equal to 3.86 meters. All right, so that's our first displacement. Our second displacement, let's use purple. Second displacement, we have D2 is 8 meters. All right, so 8 meters. And then the angle they give us is this 30 degrees here. So this will be our D2x and our D2y. So same thing, solving for D2x, that's the opposite this time. So now we have the sine of the angle is going to be D2x over D2 because D2x is opposite that angle instead of the same side this time. So you have to be really careful about what angle they're giving you. Okay, so we get D2 times the sine of the angle is equal to D2x. I just multiplied D2 times both sides. So plugging in our numbers, we get D2x is equal to D2, which is 8 meters, times the sine of 30, which is 4 meters. And then doing the same thing for D2y, we get cosine of the angle is D2y over D2. D2y is D2 times the cosine of the angle. Plugging in our numbers, D2y equals 8 meters times the cosine of 30 degrees. We get D2y is equal to 6.93 meters. And then this is really important here that you notify which direction these vectors are in. So our D2x is in the positive direction, just like our D1x is. But look at this, our D2y is in the negative direction. It's pointed downward. So I'm going to make a note for myself that this is negative. Because when I actually am going to plug this in to get the resultant y vector, that one has to be negative because it's in the negative direction. All right, last but not least, we have our D3, which is this one right here, and it only has an x component because there's no angle. So we know that our D3x is that 5 meters, but our D3y is 0. So now what we want to do, we want to get our resultant vector. So our resultant dx will be d1x plus d2x plus d3x, which is d1x, 4.6 meters, 4.6 meters, plus our d2x, which was 4 meters, plus our d3x, which is 5 meters. So we end up getting dx is equal to 13.6 meters. And then same thing for dy. dy is equal to d1y plus d2y plus d3y. So we get d1y was 3.86 meters. Plus d2y, which was a negative 6.93 meters, plus our 0, which was our d3y. So we end up getting dy is equal to negative 3.07 meters. Okay, now we want the total resultant, like magnitude of resultant vector and direction. So we need to now take these components and put them into a right triangle so we can find the magnitude of the resultant vector. So dx is positive, so I get a 13.6 meters for dx, and then the dy was negative, so notice how I put it downward, but I'm not going to actually write the negative here because I already denoted the negative with the direction. Okay, so now this here is our resultant vector, and then in order to find the magnitude, I need to use Pythagorean theorem. So we get our 13.6 squared plus 3.07 squared equals, and I'll just call that r squared for resultant. So solving for our resultant vector, I'm going to do this in my calculator, I end up getting r equals 13.9 meters. So that is our resultant vector. Now we also want to find the angle because we want to find the direction. Now you can use any of the trigonometry, you know, sine, cosine, tangent. I'm going to use tangent just because we got the two x and y component. So you're going to do the inverse, so inverse tangent, in order to find the angle, and that's going to be opposite over adjacent, so we get 3.07 over 13.6, and we end up getting that the angle is 12.7 degrees. Now for this one, because it's a negative, so technically we take the angle from the x direction usually, so this actually is going to be a negative 12.7 degrees because it is below that x-axis.